So this problem asks us to show that binary search runs in big O of log n time. And so we ask ourselves, we've heard of log n time, but what really does it mean? Binary search is kind of like, we can define it in a kind of a recurrence, in the sense that basically binary search runs a process, and then it runs a very similar process on an input that's smaller, over and over again, until we reach a base case. So the way if the way I would do this is, and the way we find the recurrence, which we went over in lecture. So we want to see what happens if our array was of size 0. And well, nothing really happens, so that's just 0. And then I like to do one more base case just to double check, and you'll see why later. But t of 1, once again, if my array n is 1, it doesn't go through the while loop, it just returns low, so that's just 1. And basically what we're learning, and if we understand how binary search works, is we pick a midpoint in the array. So let's suppose our array was of size 4. And we split it into two intervals where this might have 2 elements and this would have 2 elements. We can say is there's some constant time operation it takes for it to break the input in half, and it runs the same process on half of its input. So that's great for an even case, but for an odd case, we might actually have, if like we had 5 elements, we would have 3 elements in one interval and 2 elements in the other. So really the worst case runtime is however long it takes to run on the larger half of the 2. So we can actually fix that really easily by putting in a ceiling. And that's how we get this function and these 2 base cases, because in any recursive algorithm, we need to have a base case so it stops. So before we go further, I want to ask ourselves, well, what does it mean to run in big O of log n time? So I've put here the definition of big O, and where this is the input size and this is the runtime, where once I pick this n0 over here, everything above it, f of n will always be slightly less than or equal to d log n, where d is some constant. So in other words, binary search would run in big O of log n time if I can choose some d greater than 0 e and some n0, where for all n greater than or equal to that value, t of n is less than or equal to d log n plus e. If we look at what log n is, we can't really do log of 0. So we already have a hint that maybe we should choose our n0 to be 1. So we choose our n0 equal to 1 and then say for all n greater than or equal to 1, let's show that t of n grows in less than of d log n plus e time. And if we take a moment, what we're seeing is we have a recurrence, right? Which is up here, this t of n less than or equal to, I'll write it a little bigger, right? So we have this recurrence where it's defined in terms of itself, and we have something we want to show for all n greater than or equal to something. So that's a sign that we want to use induction. And the next thing we're going to talk about really fast is that basically in our induction, our whole point is that I want to find a D and E so that my induction is true. So we want to show that we can choose some D and E so that for all n this statement will be true. So by induction it would work. However, because we know we're going to be dealing with the ceiling in the t of n term, it might be easier if we show that t of n is less than or equal to d, the ceiling of log n plus e, and then simply say, choose your d and e to be a little bigger than what you chose for here, and it'll still work out. Because we know ceiling is going to be going to be at most like 0.5 away from whatever the full value is. So it should all work out just fine. So anyway, yeah. So let's talk about how we're going to do this with induction. So if I want to show that binary search runs in big O of log n time, and I pick my n0 equaling 1, and I want to choose my d greater than 0 in e, so this is where I'm going to keep track of what my D and E need to be so that my induction stays true the entire time. Basically, here's what we end up with. So we're like, I want to show for all n greater than or equal to 1 that t of n runs in less than or equal to d ceiling of log n plus e. And I'm going to do this by induction on n. 3 is my base case, and of course it's the smallest that we can break our problem into. And we know that our base case t of 1, in this case t of 1 equals 1. And we want to ask ourselves, well, is t of 1 less than or equal to d the ceiling of log of 1 plus e? Well, log base 2 of 1 is just 0, so this d term goes away. And so we end up asking ourselves, well, is 1 less than or equal to e? Well, certainly, it totally can if we pick our e to be greater than or equal to 1. So that's what I'm going to say here, that if I choose e greater than or equal to 1, then the base case is true. Step 4 is our inductive step. So our opponent's going to give us some array of some input size that he thinks we're not going to be able to do. And step 6 is going to go off of that, where it's just going to be what I want to show. And step 5 is going to be our inductive hypothesis. So what we can assume for all smaller n than what we're given, but bigger than our base case. And remembering our D and E is always the same as what we picked up there. So the way we're going to do this, and we want to prove, is for step 7. Well, we have cases, right? We either have n could be even or n could be odd. And if n is even, then the ceiling kind of goes away. And if n is odd, then we have to add 1, right? So let's do this in 2 cases. Let's say n is even. Well, if n is even, we still know that t of n is less than or equal to t of the ceiling of n over 2 plus c, right? And that's just our given. We then know that because n over 2 is always equal to the ceiling of itself, because n over 2 will be an integer if n is even, we can say, and from there, well, we know n over 2 is less than n, so we can actually apply our induction hypothesis to this. And once we remember our log rules, we can do this. And we can actually recall that log base 2 of 2 is just 1, so we can simplify that. And if we remember our rules about ceilings and floors, if we have an integer inside, we can actually take the integer outside of the ceiling or floor. And I'm just going to remember to distribute my d. And essentially, if I had my d and e, ideally what would happen was I would be able to simplify this further, and it would come all the way down to what I'm trying to show. So I'm going to actually write that sentence down, that if I chose, basically I would know that d of ceiling would have simplified all the way down into this if I knew what my d and e were. So what would need to be true about my d and e for this statement to be true? Well, we know our e's cancel and our d's cancel. So really what we end up being left with is d needs to be greater than or equal to c. Awesome, so there's a constraint. But we still need to check that the induction would still be true even when n is odd. So I'm going to draw a little line here. And so what we can say here is, okay, well, we can start with the same given statement. And if if n is odd, we then know that we can then say that the ceiling is going to be equal to n plus 1 over 2 plus c. And once again, we're given something that's smaller than the base case. So once again, we can apply our induction hypothesis, which tells us this. And from here, we can remember our log rules just like last time. And once again, we can take out the log base 2 of 2 because that's just 1 and distribute the d. So this is actually where it gets a little tricky, because we have to remember that n is odd. So the way I would do this is I would write out my log powers. So basically what we remember is every number that's in between these two are going to be decimals, and it goes to the next integer at powers of 2. Now log base, to have a power of 2, we would need to have an even number. Odd numbers can't be powers of 2. So if we were to plug in, if n was supposed to be odd, right, this would be when n equals 1, we would have the ceiling of log base 2 of 2, which would of course equal 1, but also the ceiling of log base 2 of 1 would also equal 1. And if we looked here, this was when n was going to equal 3, right? So we would have, and we know log base 2 of 3 plus 1, and we take the ceiling of that would be 2. Well, we also know the ceiling of log base 2 of 3 is also going to be 2, because it goes up to the next power. Therefore, what we actually know, because n is odd, we can rewrite this statement as saying, so hopefully that makes some sense. And once again, we can come back down to our same statement over here, where how can we choose our d and e for this induction part to be true? And once again, it's literally identical because we have the same equation. So what we can say here in our step 8, because our induction would be true if we choose our d greater than or equal to c and our e greater than or equal to 1, our whole induction is true. Therefore, we can say, and of course, to bring it back to our showing that it runs in big O of log n time, we can say choose your d and e to be a little bigger than that, and it would be in big O of log n time. So essentially, you're saying that I could choose my d and e if they were slightly bigger. I can also show t of n is less than or equal to d log n plus e. Therefore, basically what we can say is, therefore, I know there exists, and thus binary search runs in big O of log n time. So it's kind of a big problem, and it's easy to lose track of where we are, but essentially what we did was we found a recurrence for binary search, and usually this is given to you. You won't have to do this yourself. And from there, we understood what the definition of big O was, and how we did that was we found, well, we know that there has to be we can rewrite t of n as some function that grows at a rate slightly less than or equal to log n, some functions with d log n. And so the way we did that was we wanted to show that there exists some d and e where t of n was less than or equal to d log n plus e. And from that, the way we did that was, in order to show that for all n, because we were given some recursive function, we were able to use induction. And what we did was we half reverse engineered what our constants should be so that the induction would be true. And once we went through the induction and found how to pick our d and e, we were able to show that, therefore, binary search runs in big O of log n time.